So thank you very much. So this is the moment that you people ask questions about all the stuff that this gentleman said, which believe me, he said a few things which are interesting. So Larry, wait, sorry, before, we are short of helping staff about the microphones. So you know what? I will do the running. Yes, we have someone. So, please do your work.
For the recording for posterity,
Right,
so, you have a microphone and we take Nicholas's away.
There was one statement you made in terms of what is needed for AI that actually kind of raised my eyebrows a little bit, where you said
only one.
Only one. No, one that really jumped out. Where you said that AI doesn't need object stores, just high performance file systems. And this is, I guess, this is a little contrary to what I've been hearing.
So what I meant there, because at this point the root of all good file systems is an object store under the covers, but the sort of cloud model is you have no sort of persistent shared storage. You check your data into an object store. You move all the files into sort of a locally provisioned file system when you start running, say, your model training. And what we found is that really these, things like Lustre, EBFS, the rise of Weka, VAST, all of these shared file systems, even though there's object store technology under the covers, what you need is a large-scale parallel file system that has semantics for locking, right, where you can't, you don't have to manually manage from the application level your race conditions about who's the last writer and reader, and things like that. And that, in fact, in the AI workloads, more so than, well, we used to believe in the HPC workloads that we had very large, mostly contiguous, or at least through 2 phases of I/O. I think Alex here, we could make big contiguous reads and writes to file systems. It turns out even then that our average transaction size is like 4K to the file system. But I think with AI, we're seeing, sort of, because mostly it's sort of reading big graphs, sort of small random access to file systems. And so it sort of kills performance on some of the more traditional large-scale parallel file systems and made way for this new wave like VAST and Weka. They're optimized, but you need this sort of persistent shared storage. You can't just say, well, my instance is over, I'm going to write that out to the object store and migrate it back when you're dealing with terabytes and terabytes of training data that you're checkpointing. Yeah.
I'll ask you, but you're not saying POSIX suffices.
I'm not, although it really helps. But yes, beyond POSIX to have the things that NFS doesn't do and that the parallel file systems do, right, I think we need. Yeah.
So the next question is for Ruud, who has been texting me that this is exactly what I said last year.
Yeah, I listened.
Dan, very nice talk. I've just been waiting 40 years to take this. Because performance has always been my job. And I have a question related to that, because we're spending, it's of all ages, we're spending trillions on hardware. Meanwhile, college education is dropping behind. Nobody talks about performance anymore, as far as I know. It's not part of a curriculum. It's not even a subtopic of software engineering. You don't talk about that. Do you have any sort of hope for us that that's going to change now with what's happening in the market?
So I took these slides out, but yeah, we're going to have to create incentives to do this, right? Incentives for better software. Back when the U.S. had a government, there were some policy levers we could have pulled to incentivize better software and maybe better balance that split, which I know you have argued for, and many of us have argued for, that we don't have this balance between the investment in software and software efficiency versus the investment we make in hardware on these things, which I firmly believe in. But I will say that efficiency discussion has disappeared from most of the computer science curriculums around the world, as you have seen, in the sort of scientific community, computing community, and in the programs that have great computational science and computational engineering. It's much more alive there, just because it's how do I do things to make the problems I want to solve feasible, right? Because otherwise I don't fit in current hardware or hardware near term. And so I think Omar and Karen are giving some more algorithmic heavy talks later on where we talk about some of those things. But there are parts of the curriculum where it's not lost. It's just been lost in computer science, and we need to bring it back. And I think the way we do that in the marketplace is you create incentives, right? One is GPU time's $10 an hour right now. $8 or $10 per hour to get H100 time. I think a 8-way instance on Amazon is $98 per hour on demand for 8 GPUs. So $12 an hour. That should create an incentive, but people are going to have to start caring that my optimization. I've seen a bunch of little startups do this. We'll see if they get going. I think DeepSeek has got some attention on it, but that if we pay attention to this, we can save literally billions, trillions of dollars, as you mentioned, right? So we've thought about, changing the metric. It would take us years to do this, but we're reporting energy usage on jobs now when people run them, and stop charging by number of hours of CPU or GPU time they consume, and just do it on total joules, right?
So
I think the hope is to do green, use the green argument around making software more efficient, right? Make it more efficient because it uses less energy. May give us a new lever to pull in that sort of software optimization space.
So let's bounce in this side.
Okay, thanks for that. Really great talk. Really interesting to see. One of the points you made was back to using commodity hardware, and I'd like to ask if we actually can do that, because a lot of organizations professionally also seem to have sort of cottoned on to that, are starting to look at commodity stuff for on-prem hosting or various projects they're doing. And also in the consumer space, a lot of people are struggling to get hardware at the moment. So what's happening in the commodity space is there's such high demand there that prices are massively inflated. Stock is extremely backlogged. Here in New Zealand, we're sometimes seeing stuff that's unavailable for months on end. And what I fear is also happening is similar to what Ruud was saying. What's the impact going to be on people for education purposes or hobby purposes if this hardware is all just becoming so inaccessible? Like, is it preventing people from being able to get into this as a hobby, start to upskill, learn about the performance, and just what's the impact of that? Can we actually use commodity hardware?
Yeah, so I think one of the advantages of using commodity hardware is that although the highest end articles are often backlogged, it's hard to get H200s at the moment, right? It's going to be even harder to get Blackwells shortly, which are in sort of shipping to early customers, but in massive quantities. Heck, it's hard to get the attention of a vendor right now if you're ordering for less than $100 million. And we talk about multiple very large ones that will have sort of internal memos going around that says, if it's a customer complaining and they haven't ordered $100 million worth, just ignore it. It's not worth talking about. So 5 customers that matter that generate 90% of the revenue. But at the same time, the kind of innovations you need to do this, if you have an older, A40 card, the individual functional units are the same, right? And figuring out how to get from 10% efficiency on a modern GPU to 40% efficiency on a modern GPU takes one of a GPU made in the last 8 years, 10 years, right? You don't have to have the bleeding edge, right? So, and you don't have to have 10,000 of them to figure out that efficiency. So I think, this kind of push means you don't need all of Microsoft Azure to figure out how to make it advance in AI and algorithms, right? You can use, a couple of 5-year-old GPUs and do the same thing. And I think what I was really contrasting the commodity hardware to is there's still a push of how we're going to get more 64-bit performance, particularly among maybe my Department of Energy colleagues, right? Can we convince the vendors to do special 64-bit things for us? And we're just not going to have enough money to make them change because of that same demand curve that we're talking about, right? It used to be we could go to a vendor and say, hey, if we give you an extra $100 million in development costs, could you maybe, or $200 million in development costs, could you add these features in? I think there's still opportunity to do that around the edges, right? Maybe a better memory controller for sparse data that might apply to their bigger customers. Yeah.
NVIDIA used to sponsor this little meeting. 10 years ago, they gave away from A40.
Yeah. Yeah. But now your problem is you didn't ask them for $100 million. You asked them for like $10,000 to sponsor, and not worth their attention.
In relation to that 64-bit question, one of the interesting things that DeepSeek did when they embarrassed the highly funded startups was they packed FP8 floats into a FP32, which was the GPU they were using. And when they were doing the training, what they were doing is they were striping those FP8s, and then they were using the full 32-bit precision for the compute. They were just using the FP8 packing for improving the bandwidth. Is that the sort of thing that you might be able to convince GPU manufacturers to kind of embrace, and that would be a good reason to have 64-bit?
Yeah, I mean, potentially, yeah. If they're doing 4-bit operations for the mass markets, right, they're still probably using a long vector register to do them all. Right? There's just a few microcontroller signals we might need to add, right, to be able to do a reasonable 64-bit or to chain. Again, we can do it all in software, but it's expensive. If they'd add just a little bit of microcontrol in those 16-bit, matrix units that they're doing most of the AI in, the bfloat 16. What does NVIDIA call their matrix unit now? I forgot the word, but those matrix operations, they could just add a little bit of microcontrollers. We might be able to chain them together better. And then packing lower precision into higher precision is unfortunately easier than going the other way around. But I think that's the kind of creativity we're going to need to get from both the hardware community and the software community to sort of figure out how to use this stuff.
Thanks, Dan. I guess I'm interested in the, you talked about commodity hardware. I'm interested in commodity software. And I guess the last couple of weeks we've had GitHub Copilot agents come out. And so I'm wondering if you just want to have a wee think about the impact of these AI agents on developing high performance scientific software. And I guess my question is when are we going to see the first AI scientific software agent at TAC?
Yeah. We already have a TAC bot. It's more for doing user support than for generating code, but most of my programmers are doing, sort of AI assisted tools at this point. And this is, back to one of those first slides I had where the disruption isn't necessarily, the disruption in science is not necessarily AI replacing simulation, but it's AI impacting other parts of the workflow. I do think AI-based code generation has a lot of potential. But from what I've seen, obviously limited exposure at this point. I don't get to code very much. And just from what I've heard from my team, we're using a lot of AI to generate sort of small bits of the code, but we still need humans to debug, stitch it all together, right? And worry about these sort of efficiency things. But, can it find a better inner loop and do an inner loop optimization for you? Yeah, it probably can. Can you, can it do all the glue functions that run once or twice, not a billion times? And, but save you a lot of programming time? Yes, it can. I don't know if we can tell agents at this point, build me a better CFD simulation of this particular geometry than you can do with bespoke models now. But I think it will play a bigger and bigger role. And we're installing some inferencing hardware this month actually, so that we can have always on AI models. Sorry, there's a light between me and you. You're just sort of a hazy thing out there. You might have a halo, so enjoy. But so the idea is that we have several hundred models that are just always on, available for inference. We can do some of these things. We've seen like inferencing between time steps and simulations and stuff start to work. So I don't know, but I think pretty soon. I think it will have a big impact. Yeah.
Those agents would close using like polls rather than generating code, and it's no big taking. So you get to a point where actually your AI agent can help us. It's not just spitting out some fortran that can help you design.
Yeah.
Mm-hmm.
Yeah, it's doing the orchestration.
Mm-hmm. Let's keep it.
Like I said, I didn't get into our hardware platforms and plans, but this new inferencing hardware so that we can have models that are always on, right? So that you can, from your workflow, just say, I need to inference from this model and get an answer rather than embed everything into your code and do it as a one-off every time you run a job. Yeah, so it's toward that agent idea. Yeah.
Couple of last questions, DK, and then Omar.
Dan, thanks for the great talk. I think my question is related to the previous question you just asked. As you mentioned, the hardware will continue with the 3, 16, 8, 4 kind of things.
You got to stop by 1, I figure.
Whatever the end. Yeah. The algorithms you said, like some people have started working, but the question is, can real parallel algorithms which have been developed for like last 30, 40 years, can they be converted to work with lower precision?
I mean, my guess is not all of them, but more than we think, right?
Okay.
And I base that on having the same arguments about vector supercomputers in the 80s, right? We'll never get them to work on microprocessors. We'll never get them to work in RISC microprocessors, right? And then it turns out, the famous debate, Danny Hillis, Seymour Cray on stage in the 80s talking about, big processors versus distributed clusters. And I think Seymour said, if you had to plow a field, would you rather have it pulled by 2 strong oxen or 1,000 small chickens, right, pulling your plow? And it turned out the right answer has become 1,000 chickens, right? Because we have these giant clusters and they're used pretty widely. And it's because, although we understood things like strong scaling, we didn't understand how much scaling up the problem size helps with the parallelism and having this sort of available data parallelism. So, every time we've been skeptical that we can't make the algorithms work, again, there's always at the time it was like, well, maybe 20% of algorithms can run on these fancy commodity clusters, but 80% will be on big custom hardware supercomputers, right? And it turned out to be the opposite. And it's hard to buy a big silicon there's still some NEC vector processors out there, I think, in Japan, but it's hard to do, right? I mean, big praise now are commodity processor based, right? So
I have just to follow up to that.
I think it's more than we think, but we have to actually work at it to figure that out.
Okay. So if that cannot be done, like let's say for the 80% which cannot be done, is there a need for like a floating point emulation? The very old days, like emulating or some kind of a software libraries which will give you the same precision but on the modern hardware.
Yeah, I absolutely think so. I mean, there's still that old, I can't remember the name of the library, but there's an arbitrary precision library, right? That we used to do, it's like, hey, take your 64-bit registers and do 128 or do 256. In the rare cases that you need it, they did it through software emulation that was, 8, 10, 12 times slower. But if you're, again, right now the multiple from 16-bit to 64-bit on GPUs is 30. So if it's 10 times slower to use 16-bit to emulate 64-bit, but you have 30 times the performance, you still end up going 3 times faster, right? So on the same piece of hardware. So I do absolutely think we need to revisit the arbitrary precision things from the days of yore and emulate the precision. I just worry that we're going to get to so few bits, right? I mean, I need an exponent and a mantissa. That's at least 2, right? I mean, I've seen, I think, some of the very low precision, they're just using an implied 1 as the mantissa. So you just have exponent bits, right? You have 1, 10, 100, or 1,000, right? So, and for AI that's good enough, we need more than that. But could we use the 16-bit circuits to get to 64? Yeah, with some of the software emulation, I think we can.
Okay.
So
Thank you.
Yeah, thanks, DK.
About 20 years ago, I met Professor Patterson from Stanford.
Wrote a textbook.
He wrote a book. And he was mentioning the 1,000 chickens analogy at the time, but he was also promoting something new about multi-core, because laptops that melt in your lap is not a good marketing proposition. So I want to believe that 5 years later, when he started with RISC-V, had something to do with that. So the context that I'm making is that things doesn't happen in a vacuum. It's an evolution.
Yeah.
So,
and I mean, right now, it's do you buy 1,000 H100s or 8 Cerebus chips, right? I mean, it's the same debate, right? Happening later. But we've decided we will melt your laptops. Yeah. The server power, we're just going, Blackwell modules are 2,700 watts and they're this big. So figure it out.
Great points, Dan, particularly about the algorithmic innovation that needs to happen, that it is happening, that's going to disrupt completely the landscape that we have today. Just wanted to emphasize or add on the optimization front, optimization algorithms. I don't think, in 10 years, we're not going to be seeing Atom. There's no way. This is in many other areas that use optimization, optimal control, optimal design, inverse problems. Nobody uses first order methods. These are 40s technology, and I don't mean 1940s, 1840s. This is totally steepest descent. Of course, there are modern versions, Robinson, Monroe, stochastic gradients, but this is all, half-century old methods. There will be changes as we speak. There's some grad students sitting in a cubicle in some basement working out some new high-order optimization algorithm, testing it out. There are challenges and difficulties, and in particular, that list of new algorithmic innovations that you're talking about, high order and sparse matrix exploitation and so on. The challenge is that a number of these are not necessarily friendly to high throughput data parallel architectures. The more algorithmically efficient the algorithm becomes, sometimes, in fact, often,
the computational efficiency goes down.
Computational efficiency goes down because it's indirect addressing, it's unstructured computation, adaptivity, etc. So we have to find the right balance. We're sort of stuck following, we're stuck with the hardware we get, I suppose. But I think things are going to radically change in the next 10 years. And I wouldn't be investing in nuclear power plants. I mean, we can invest in them for other reasons, but I think we're going to, the deep.
So we bet it.
By the way, the top performing stock in the S&P 500 last year was not NVIDIA. It was a utility company that builds power for data centers based in Dallas.
Maybe I should be investing.
So, well, you should. But again, it doesn't mean it's the right answer, just where the market has gone, right? But no, I totally agree that things are going to change. But it is hard and requires this investment in algorithms, right? That we don't seem to be making at a sufficient scale, given how much money we're throwing at AI right now. So, but yes, and to the 1840s, I used to tell my students in digital circuits, right, that George Boole invented Boolean algebra in 1854, but it took another 100 years for us to build the gates to run it on digital circuits. So you can still make those innovations if you're a grad student sitting in a lab. The lesson is you'll probably be dead before it gets used. But you won't make money at it, but it's going to change the world at some point. So we all know Boolean algebra. Not everybody knew George in the 1850s.
Right. So, English school teacher.
Please join me in saying thank you to Dan.
Thank you.